Matthews, Gatos here. In this video we are going to do section 6.4, but before I get to that we're going to review 6.3. So in this one here we're given a diploma question where we're given an identity and we're just asked to find the non-permissible values. So let's look at the denominators here. 1 minus cos squared theta cannot equal 0. So let's solve this one first. I'm going to add cos squared theta to both sides. And then I'm going to take the square root of both sides. Now remember, when you take the square root, it has to be plus or minus, because 1 times 1 is 1, but negative 1 times negative 1 also 1. So that means that plus or minus 1 is equal to cos theta. Now over here in the next one, I want that sine squared theta can't equal 0. Take the square root of both sides, and I don't have to do plus minus because it's just 0. So sine theta cannot equal 0. So we have restrictions of cos can't be 1 and negative 1, and sine can't be 0. So you can look at your unit circle. Sine is your y coordinate, and so you don't want sine to be equal to 0. So that is going to happen at 0 and 2 pi, and it's also going to happen at pi. So that means that theta cannot equal to 0, pi, or 2 pi. Now looking at where cosine is equal to 1, cosine is equal to plus and minus 1 at the x-intercepts. So here it's at 1 and here it's at negative 1. So it looks like they have the exact same restrictions. So these restrictions are the same for both. So it's starting at 0 every pi and repeating by multiples of pi. So I can just say that it's pi n, where n is an integer, meaning positive and negative. Okay, in the next one, we want to verify the identity for 2 pi over 3, and by doing so, what is the exact value of each side? So I know it asks to, both sides are equal. You could just technically find one of the sides. I'm going to find both just to make sure I'm correct. So since it's for 2 pi over 3, I go on my unit circle and I look at the coordinate for 2 pi over 3. So the x coordinate will be cosine, and the y coordinate will be sine, alphabetical order. And then we just plug it in and do some number crunching. So sine of x, root 3 over 2, over 1 minus cos of x should be equal to 1 plus cos of x over sine of x. Okay, so I have a whole bunch of 2's going on here. Let's just simplify first before I get rid of all my fractions. So root 3 over 2, 1 plus negative 3 halves, or 1 half is 3 halves. 1 plus negative a half is a half. Okay, so to get rid of all these divide by 2's, I will multiply the numerator and the denominator by 2, because 2 over 2 is just 1. And I'm left with root 3 over 3 equals 2, 1 over root 3. So those don't appear at first look to be equal, but if I were to rationalize my denominator, multiply top and bottom by root 3, I would get root 3 over 3 equals root 3 over 3. So now that I have the same on both sides, I'm convinced that my answer is correct, and my answer would be D. Okay, in this section we're going to look at solving trig equations. So this is where chapter 6.1 and 6.2 are going to come in, but also the steps that we used in 6.3 are going to help us get ready to solve trig equations. So we're going to use those same strategies we used in the last lesson, 6.3, to write trig expressions in terms of one trig function if possible. And of course, this time we're going to state the non-permissible values because we're not proving, because we need to check the solution that we get in the last step against the non-permissible values and, of course, in the calculator. We're going to state our solution within the domain that's specified, and if there is no domain, we're going to do a general solution. So all the solutions from 0 up to the period and add on multiples of the period. So let's go ahead and try one. So I have 2 cos squared minus 3 sine x equals 0 between 0 and not including pi, so 0 up to but not including pi. So specific domain means specific solution. So I'm going to rewrite cos squared in terms of sine, because I know that cos squared plus sine squared equals 1. So cos squared, it's one of those rearrangements of the Pythagorean identity that we did, is going to be 1 minus sine squared. So instead of cos squared, I'm going to use 1 minus sine squared. So 2 cos squared, or 2 1 minus sine squareds, minus 3 sine x equals 0. So now you see I have a quadratic, but it's all in terms of sine. So distributing the 2 inside the brackets, I get this. So let's rearrange it in highest power of x down. So negative 2 sine squared x minus 3 sine x plus 2 equals 0. And then I'll just divide all my terms by negative 1 to make my leading coefficient positive. I can do that because it's an equation. I'm not changing it because I'm doing it to both sides. So I end up with 2 sine squared plus 3 sine x minus 2 equals 0. And then I'm just going to go ahead and factor this. So 2 sine x, 2 and 1, and then I'll go plus and minus equals 0. Okay, so now that I have it factored, I just set each factor equal to 0 and solve for x. So here I'll add 1 and divide by 2 to get that sine x is a half. And here I'll subtract 2 from both sides to get sine x is negative 2. Now, hopefully you recognize the range of sine x is between negative 1 and 1, so it was actually impossible to have a sine value that is negative 2. So the only solution I have is sine x equals to a half. So I can go again to my unit circle. I'm going to look at where sine is equal to a half. Sine's positive in quadrants 1 and 2. So I'm looking at where it's a half, the y coordinate. And what were we looking at? We're looking at radians. So the first one is pi over 6. And the next time it's a half is over here at 5 pi over 6. So that would be my solution. Let me just get that out of the way now. Okay, so my solution pi over 6 and 5 pi over 6. And that satisfies my domain restriction between 0 and pi. So the next place that I'm going to check it is in my calculator. I started at pi over 6, and I'm looking at where it's equal to 0. Now, because I'm starting with pi's, of course, my radians have to be my mode. So it's equal to 0 here, and 5 pi over 6 also equals 0 here, so I know I did it correctly. Okay, for this one here, sine x minus root 3 cos x equals to 0. From 0 to 360, again, specific solution. So it doesn't look like there's anything that I can factor here. There's no common terms. So a strategy I have students tell me is, why don't you just divide everything by sine so that you could get a cotan, or divide everything by cosine so you can get a cotan. And I think that's a good strategy, but it's just, we need to approach it from a different angle, because in math you can never ever divide both sides of an equation by a variable. So if I can't divide both sides of an equation by an x, I certainly can't divide both sides of an equation by a sine x. So we have to use a different strategy. So even though there is no GCF, what I'm going to do is factor either a sine or a cosine, as mentioned before, leaving either a tan or a cotan. We're going to do both so that you can see that they both actually work. So let's look at option number 1. In option number 1, I will factor a sine. So I'm going to take a sine x out, which just means I'm factoring both terms by sine. Okay, now because I am factoring both sides of sine, I'm introducing a non-permissible value here. So I just want to note over here that sine x can't equal 0. Okay, so dividing both sides by sine. Sine divided by sine is 1, minus root 3. Cos divided by sine is cotan, and that's equal to 0. So now I've factored it, and I'm going to set each factor to 0. So sine x can equal 0, or 1 minus root 3 cotan x equals 0. Well, we just said that sine x can't be 0, so that's not a solution because it will introduce a non-permissible value. So over here, let's add root 3 cotan to both sides, and then I'll divide both sides by root 3. Okay, so I have 1 over root 3 equals to cotan x. Now cotan is the ratio of cos over sine, and cotan is positive. So I'm looking at the ratio of cosine over sine in quadrants number 1 and 3, because that's when cotan is positive. So let's go to our unit circle. In quadrants 1 and 3, where is the ratio 1 over root 3? Well, I can see right here it's 1 over root 3, and that's going to happen at 60 degrees. And then over here, it's also negative 1 over negative root 3. That's 1 over root 3 because two negatives make a positive. So that happens at 240. Now, let's pretend for a minute you forgot your restriction that sine x can't be 0. That's okay, because I'm going to show you in the calculator that you can catch that. So let's pretend you didn't notice that. Well, where is sine x equal to 0? That's the y coordinate. Sine x is equal to 0 here and here. So let's say you forgot that. That's like 0 and 180 and 360, so on. Okay? I'll show you that you're going to catch it in the calculator. Now, it doesn't equal to 360, so we'll cross that one off because it's less than. Let's check the solutions for 0, 180, 60, and 240 and see what we come up with. Okay, so first of all, our domain was in degrees, so you need to change your calculator back to degrees, because if you don't, you're going to have a rad time. Normally, I'm all in favor of having a rad time, but I don't want to be in radians in this situation. So let's look at, say you forgot the restriction of 0 and 180. You can catch it in your calculator because you can clearly see it does not equal to 0. And here it does not equal to 0. So these are not solutions. So if you don't catch it with the restriction, you'll catch it in the calculator. You would go back and say x can't equal those. But here at 60 degrees, it's equal to 0. And at 240, it's also equal to 0. Okay, let's try option number 2. So we factored out sine. This time, let's factor out cosine. So we're going to factor out a cos x, which just means divide both terms by a cos x. And then let's look at what we're left with. So sine over cosine is tangent minus the cosines cancel. Root 3 equals 0. Again, because I'm dividing by 0, I need to state my restrictions that cos x can't be 0. So let's set each factor equal to 0. So cos x equals 0. Or tan x minus root 3 equals 0. So we already said cos x can't be 0, so I know there's no solution there. And here I'll add root 3 to both sides to get tan of x equals root 3. So to help you find the solutions there, let's just make it over 1, so it's easier to find that on the unit circle. Now tan is positive in quadrants number 1 and 3, and we're looking for root 3 over 1. I bet you're going to have the same solutions that we did for cotan, because cotan was 1 over root 3, so it really should be the same. But let's just double check. So over here on my unit circle, I'm looking where tan of x is equal to root 3 over 1. So y coordinate over x coordinate. So root 3 over 1 right there at 60. Yeah, looks like I'm getting the same. And then over here at 240. I have a negative root 3 over a negative 1. Two negatives make a positive. Okay, so I know those are my solutions. Again, let's say you forgot that cos can't be 0. So where cosine is 0, that's the x coordinate can't be 0. That's going to happen at 90 and 270, because you can see cosine is 0 and 0. So let's pretend we didn't notice that. I know you guys would never make that mistake. That's probably a mistake I would make, but I would catch it in the calculator. So let's look. We're going to check 60, 90, 270, and 240 in the calculator and see what happens. So I'm looking for 0 again. Mode is in degrees. So again, you see 60 is 0. Yay. 240 is 0. 90, not 0. It's 1. 270, not 0. Negative 1. So if you don't catch it in the first step, you'll catch it in the second one. You'll get there. So that would be my solution again, 60 or 240, depending on which way you factor. So that's a neat little trick you can kind of keep in your idea bag. So let's look at this one here. Solve the following: sine of 2x plus cos of x equals 0 between 0 and up to but not including 2 pi. So you can see I have the formula there for sine of 2x, so let's write that out. So I've got 2 sine x cos x plus cos x equals 0. So I'm going to factor out a cos x. And then set each factor equal to 0. So cos x equals 0, or 2 sine x plus 1 equals 0. And subtracting 1, dividing by 2, I get negative a half. So I'm looking at all my solutions from 0 to 2 pi. So let's take this out here. Okay, so where is cosine 0? That's the x-coordinate. It's 0 at pi over 2 and 3 pi over 2. And then sine x equaling to negative a half. Sine is negative in quadrants 3 and 4. And negative a half for the y-coordinate right there at at 7 pi over 6. And then also negative here at 11 pi over 6. Okay, so it looks like those are all my solutions, but I'm always going to check in the calculator. So I'm going to put this into y1, and I'm going to do the table for each one of those to see if it's equal to 0. So there's my equation. I'm in radians, and you can see at pi over 2 it's equal to 0, 3 pi over 2 it's 0, 7 pi over 6, and 11 pi over 6. I have this weird number. We talked about this before. This is 0 in disguise. What I mean by that is it is in scientific notation, so it's like 2 times 10 to the exponent of negative 13. That's a 0 with 12 zeros. 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then a 2. So what I mean by 0 in disguise, let's just call that 0. And I can say that it's equal for all of them. Okay? So the check's super, super important. Let's try one with a notice here, I don't have a domain restriction, which means I am dealing with a general solution. So if it doesn't specify degrees or radians, it's like when you call in for customer service, press 1 for degrees, press 2 for radians. I'm pressing 1 for degrees because degrees is a little easier for me. Don't know about you, but given the choice, I'll work in degrees. So we're going to do a general solution in degrees. So cos of 2x is unique because it has 3 different formulas to choose from. Let's go through each one. If I use the first formula, I would introduce a sine squared. Don't want to do that. I only have coses. Let's stick with coses. Formula 2, that one looks good because it's just coses. Formula 3, nope, I don't want to introduce a sine squared. So keep it in terms of one variable if you can. So I'm going to use this one here in place of cos 2x. Okay, I have a quadratic, so I'm going to set it equal to 0 by subtracting cos x from both sides. And then I'm going to factor. Okay, so this is minus and this is plus. So here I have 2 cos x plus 1 equals 0. So subtracting 1 and dividing by 2, cos is negative a half. And here I have cos x minus 1 equals 0. Adding 1 to both sides, I have cos x equals 1. So we're doing this as a general solution in degrees. I'm just going to make this, oh my gosh, where does it end? There it is. I'm going to make my little cartoon smaller. Do you like her? I made her myself, including the high heels and the little rosy cheeks. I think that's pretty creative on my part. I could never draw that, but you know, I can make it on the computer. Okay, so I'm looking for negative a half and 1. So back onto my unit circle. Where is cosine 1? Well, that is an x coordinate, and an x coordinate is 1 right here at 0 and 2 pi. Okay, so, oh no, we decided we were doing degrees. Jeez. There we go, 0 and 360. So I'm going to say 360n, multiples of 360. So 0, 360, and around and around and around. Where is cosine equal to negative a half? So x coordinate negative in quadrants number 2, right here at 120. And also in quadrant number 3, and that is right here at 240. So my first solution starts at 120. I have to go all the way around the circle to find it again. Same thing with 240. So those are all of my solutions, and for each one of those I will say n is an integer, so I get positive and negative angles. So to check those in the calculator, let's just check 360, 120, and 240, because if it's true for those, it will be true for every coterminal angle as well. So at 120, you can see y1, y2 are the same. At 240, they're the same. And at 360, they are the same. So that tells me that all of my solutions are correct. So to summarize, I want you guys to try as as much as possible to simplify the equation in terms of one trig function, sine or cos preferably. Always state your non-permissible values because you're going to check your answer against those, but also as your safety net, use your graphing calculator to check. Make sure your calculator is in the correct mode, degrees or radians, and always state your solution within the domain. No domain specified. You want to use a general solution. So be on the lookout for all of those tips. Also be on the lookout for a math gang that we have running around the neighborhoods. It's a trig gang, and I want you to be aware of their gang sign. Their gang sign. Sinusoidal trig gang. No? Okay. So I want you guys to do your practice questions. Do number 1 in my notes. There's a couple parts to that. Check my solutions on D12, of course, and then you can move on to your textbook questions. So I hope this video helped, and I look forward to seeing you for the next.